Hello everyone. In this video I'll be going over 2.3 and 3.1. This will actually be the last content before the first exam. You'll see another lecture video, the practice exam for exam 1, but no new material after this one. Of course, after the first exam we'll have new material. So in 2.3, we're reinforcing the addition property of equality and the multiplication property of equality. Those are basically the two tools. So the addition property says if you have two things being equal, then you're allowed to add the same thing on both sides, and you still have equality. This equal sign is still true. Based on the addition property of equality, for free, you get basically the subtraction property of equality, if you will. So you can subtract also. You'd have to do that in the same order, but you can do that. Also, we need another tool often. So the multiplication property of equality says if two things are equal, then you're allowed to multiply by a non-zero number. Looks like I got that wrong, didn't I? So this should be not an A, there should just be a B and a C over here. Sorry about that. So you're allowed to multiply a number as long as it's not zero, right? The C can't be zero. Because of that, you also kind of get the division property of equality, right? So if A equals B, then you'd be allowed to divide A by C as long as it's not zero. You can do that on both sides, and you should still have equality. So that's just a summary of the properties of equality that we've seen. These properties allow us to solve equations. So we have a linear equation here, and it says solve each equation, check your answer. So you want to combine like terms, you want to collect all variable terms on one side and all pure number terms on the other. So I'm just going to decide to move all of the pure number terms to the right and all the variable terms to the left. So I'm going to subtract 80 as a first step. So I'm allowed to do that based on the addition property of equality. So I'll have 4x. Now I have 0 on the left, so I just won't write anything more. And then I have equals 2x minus 40. Now I want to get these x's together. I'll subtract 2x. Again, that's the addition property of equality. And now to undo this multiply, I'm going to divide by 2. So this is the multiplication property of equality, really. So x would be negative 20. And just as a check, because it did want us to check this, so we would be claiming that 4 times negative 20, right? So I'm taking my proposed solution and plugging it back into the original. So 4 times negative 20 plus 80, are you equal to, I'll write a question mark, 2 times negative 20, right? Also putting negative 20 here for x, any occurrence of x. So this looks like negative 80 plus 80, right? That would be a 0 on the left. This would be negative 40 plus 40, so 0 does equal 0. That tells me that's a true solution, right? This is a true statement. So this tells me that this is indeed the solution here. Okay, I'm gonna turn the page. Let's go to one with some fractions here. I'll go to page 27. I'll leave this one for you, but I'll go down here and do this one. We'll solve for C, it looks like this time. So, yeah, one way I can approach this is to clear out this equation of the fractions. So one way to do that would be to multiply through by a number such that all these denominators evenly divide into that number. So it's looking like if I take the number 20, so if I multiply through by 20 on both sides, I can do that by the multiplication property of equality. What I'd have is 20 over 2 on the left, still times c plus 3. And then on the right, I still have equals. I'll have 20 times 2 is 40 divided by 5. And then I'll still have that c. And then 20 times 3 is 60. So I'll have minus 60 over 4. And then the purpose of that 20 is all of these numbers, the 2, the 5, and the 4, all evenly divide into that 20. So at this step here, we can see, oh, I just have a 10 and then times c plus 3. I still need to do that. Equals 40 divided by 5. Feel free to use your calculator on stuff like that. I did 40 divided by 4. Let's try that again. So we get an 8. So that'll be an 8c minus 60 divided by 4, 15. So this equation here that I just wrote is exactly the same actually as the original one, except it just doesn't have any annoying fractions, right? So this particular 20 in this case, it's not always going to be 20, right? So you'll need to look at what denominators you have. So the only denominator you have here is a 4. So you could start this one by multiplying through by 4. So now I need to distribute. This is the distribution property. So I'll distribute that 10. I'll get 10c plus 30 equals 8c minus 15. And again, we're combining like terms. I'll go ahead and subtract 30 to combine it with the negative 15. And I need to get these like terms together here. And then divide. So it looks like negative 45 divided by 2. If you type that in, it'll just say negative 45 over 2. And then if you press this button, S to D, it'll give you the decimal version if you prefer that. Okay. And of course you could check it. I'm not going to do that in this case. But you could now plug in this number for C and make sure you get the same output on both sides. Okay. I'll go ahead and go to page 29 actually. Let's see what the instruction was. It says on page 28, solve. If the equation has no solution, write no solution. If it is an identity, write all real numbers. So for the identity, you'll see something obviously true. What I mean is like you'll try to solve the equation and then you'll get down to something like 4 equals 4. So if you try to solve one of these and you get an obviously true statement, then all real numbers would solve it. Every number works in that case. When it's a no solution case, you'll have something obviously false. Arise just out of the process of attempting to solve. So what I mean by that is you'll have like 2 equals 3. 2 does not equal 3. That's what I mean by obviously false. So this would be no solution. We call those inconsistent, but I don't think you need to worry about that. So I'm gonna go actually to part 3 of that type of problem over here, just to get a little more fraction help. On this one, I'm gonna choose to do something slightly different. So I'm not gonna multiply through by 2. I'm just gonna combine like terms. I get 2x plus 7 on the left. And then I can just go ahead and distribute that 1/2. Half of 4x would be 2x. Half of 12 is 6. Right, combine like terms. So I'll have 2x plus 7 equals 2x plus 7. Notice what's happening here is you have the same thing on both sides, right? If you combine like terms, what ends up happening is you get this obviously true statement, 0 equals 0. So this would be all real numbers. Every number you try will work. Okay. I'm going to go on to 3.1 actually now. So graphing. Graphing is important. I want to spend a good amount of time here. Here's a question. Can you think of 2 numbers such that when added, their sum is 10? In other words, if you represent these numbers as x and y, this would be the equation that one could write down. Right, so a number plus another number is 10. This is just the algebra behind this statement up here. So yeah, you can find these. Just as somewhere to begin, I could take like x to be 0 and y to be 10. Right, 0 plus 10 equals 10. I could take x equals 5 and y equals 5. I could take x equals 4 and y equals 6. X equals 3, y equals 7. X equals negative 10, right? What does y have to be? Positive 20. I could continue this list for a long time, right? You could do, let's see, 5.5 and 4.5. Negative 1.1 and 11.1. Negative 1.01 and 11.01. So how many are there? You know, how many can we find? There are infinitely many. Okay, so let's plot some of these. Maybe I'll just write down a few more. Let's see. I guess this is good. We'll just plot some of these. Okay, so on the next page, it says plot some of the pairs you found previously, basically. Okay. So this will be my x, this will be my y. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is the 0.55. So that would be one of our pairs, right? We had, maybe I'll just make a list here. We had 5, 5 was one of our options. We had 3, 7, 4, 6. You could switch that. These would be numbers such that x plus y equals 10, right? That's the equation we're talking about. So 4, 6 would actually be right here. 6, 4 would actually be right here. 7, 3 would actually be right there. And 3, 7 would actually be right there. It is not a coincidence that all of these are falling in a line. And in fact, every solution that you find to this equation would land on this line that's being implied by these points. So when you're finding solutions to this equation, you're finding points that lie on a common line. That common line is a visual description of infinitely many solutions to this equation. And that's what a graph is. So when I actually graph this, I need to grab some kind of straight edge, maybe a ruler, and imply all of those points. And I do so with that line and this set of arrows. So these are only 5 of infinitely many solutions, right, to this equation here. You can find some strange ones. So when you're graphing, so keep in mind, we just graphed this equation, but a graph is a visual representation of infinitely many solutions of an equation, right? Some equation of interest. So when you're graphing, you're making a picture of solutions. That's all you're doing. I wanted to make that evident. I know sometimes you can just graph and not know what the heck you're doing. So hopefully that helps. Example 7, so in that vein then, determine whether each ordered pair is a solution. So if you're a solution, that means that when plugged into the equation, you provide a true statement, right? So just going back here for a moment. So what is this point? That is the point 1, 2, 3, 4, 2, right? 4, 2. So 4, 2 is not on the graph of this equation. Why? Well, because 4 plus 2 does not equal 10. Right? This point over here, maybe this one implied, that one, I'm thinking of the point 10, 0. 10, 0 is on there because 10 plus 0 is 10. Right? So this is providing a true statement when plugged in. This is providing a false statement when plugged in. Therefore, this is not a solution to the equation, and that's why it's not on the graph. So what I'll do here is plug this in as x, plug this in as y. If it's true, then yes, this is a solution to the equation. So 3, right, plugging in 3 for x, minus 3 times negative 2, RU equal to 9. If this is true, then the answer to this is yes, right, this part. So 3 plus 6, right, negative times a negative, this turns into plus 6. So this is 9 equals 9, yes. All right, try this one. It's always XY, like the alphabet, in that order. So I'll go negative 2, right, plugging that in for x, minus 3 times 3, RU equal to 9. So negative 2 minus 9, this would be negative 11 equals 9. That is false. So I would say no. So let's just graph one. And that'll be the end of this video here. But try to generalize this strategy here. So this is called the point plotting method. So that's what I'm going to teach at least right now. It's up here at the top of the page, by the way, but I'm just going to do this one. So what you do is you basically pick one of the variables and you calculate the other. So point plotting. So I'm going to pick x's in this case and then calculate the y that results. So I'll just do like -2, 0, and 2. Something kind of simple. For x, I'm going to plug those in. What I'm doing by doing that is developing solutions to the equation, right? If you're developing solutions to the equation, that means you're developing points on the graph. Okay, so I'll go ahead and do that. Let's plug in -2. We have 3 times -2 minus 2. This would be -8. 3 times 0 minus 2, this would be -2, right? So x equals 0, y equals -2. 2, plug in a 2, we get 6 minus 2, this is 4. So those are my points, and now I'm going to plot them. So -2, -8. Let's see, 1, 2, 3, 4, 5, 6, 7. I guess I went a little bit off the page there. Maybe a little bit off the screen as well. 0, -2, and then 2, 4. Is that 4? Oops. So they're appearing in this line, right? So I'll go ahead and grab just something with a straight edge. I'm just using an external hard drive. And then include those arrows, right? Those arrows. That is the graph in full. Okay. I will be posting the solutions to this set of notes, right? Of course, alongside the video. Have a good one. I'll talk to you next time. Bye-bye.